In this video, we're going to let X be an accumulation point of the set M. And in the last video, we proved that M contains at least 3 points. And we did this by found a point inside it, that is M1. Then we found a smaller delta ball that didn't contain M1, and that smaller delta ball, shown in white, had to contain M2. And then we found yet another smaller delta ball, which is drawn in brown, and that smaller delta ball had to contain a point M3. Obviously, this kind of an argument can be continued. Now that we have M3, we can find a small delta ball that is too small to contain M3, but contains X because M3 was not equal to X, and because X is an accumulation point that says there is an M4 inside M such that M4 belongs to this new delta ball, and M4 is not equal to X. So M4 is somewhere, let's put it there. But then I can find a delta ball that does not contain M4. So this is my 5th delta ball. So it is that delta ball. But because X is an accumulation point, there is an M5 inside M such that M5 is inside this new tiny delta ball, and M5 is not equal to X, and that should have been an X. And the process so here's M5, and obviously we ought to be able to continue this process on forever. And if we did, we ought to get an infinite set of elements inside the set M. But now it's not a mathematical proof if we say, and just continue this forever. So what I want to do at this point is I want to state what we have as a conjecture. Our conjecture is, if the set M has an accumulation point, then M is an infinite set. Now, the way we're going to prove this conjecture is we're going to use mathematical induction. The idea here is that we want to prove that this process of building these nested delta balls never ends. And if it never ends, then we do indeed get an infinite set, an infinite subset of points all belonging to M. Now, an induction proof requires a base step and an induction step. The base step is simply the previous video. So the proof of our conjecture is by induction. And we want to observe that the base step, and actually it's base steps because I've done several of them, is the previous video. Now what I want to do is I want to state the induction hypothesis very carefully, and then I want to state the induction goal, the thing that I want to prove in the induction step. For the hypothesis, we are going to assume that we have created a set of nested delta balls, and these are going to look like my initial delta ball, which contains the next delta ball, which contains the next delta ball, all the way up to it finally contains the last delta ball that we currently have, which is our kth delta ball, the ball centered at X of radius delta K. And we are also going to assume that we have a sequence of distinct points in M, namely M1, M2, M3, all the way up to MK, where we know the following stuff about the M's. we know that M1 belongs to the first delta ball, and M1, and let me clean up my handwriting there, M1 does not belong to the second delta ball. And M2 belongs to the second delta ball, and M2 does not belong to the third delta ball. And this continues until we get to the second to last M, Mk minus 1, belongs to the delta ball with radius delta k minus 1, but it does not belong to the last of our delta balls. And finally, we know that Mk belongs to the last, the smallest of the delta balls. That's the end of our induction hypothesis. The goal is to use that nasty induction hypothesis to show we can find an Mk plus 1 that belongs to M, and Mk plus 1 is not equal to any of our previous M's. So it's not equal to Mi for I equal 1, 2, all the way up to k. So that's what our goal is. Now, in order to do this, what I'm going to do is I'm going to draw the number line. So let's draw a number line. So here's our number line. And we know that x is somewhere. And we also have that those last two delta balls. So here's the delta ball with radius delta k minus 1. And what I know is Mk minus 1 lives in there. And then I have a delta ball that's just a little bit too small to contain that one. So this delta ball is the one of radius k. And Mk is somewhere inside this ball, and I know that Mk is not equal to x. And because I know that Mk is not equal to x, what do I know? Well, I know there exists a delta ball centered at x, and its radius is going to be called delta k plus 1. And this delta ball is so small that Mk does not belong to it. So this ball here is this most recent ball. But x is an accumulation point for set M, and this delta ball is an open interval containing x. And because it's an open interval containing x, there exists an M, and I'm going to call it Mk plus 1, such that Mk plus 1 belongs to M, and Mk plus 1 belongs to my smallest delta ball, and Mk plus 1 is not equal to x. So it's somewhere in here. So what this means is that we can always find one more point inside set M in the next smaller delta ball centered at x. And what this means is that we can construct Mk plus 1 given M1, M2, all the way up to Mk. Now, it's also important to finally note that there are new point M, Mk plus 1 cannot be equal to any of the previous M's all the way up to k, because mi is not going to be inside this tiny little delta ball, because this tiny little delta ball is smaller than the distance between delta k plus 1 is smaller than the distance between x and mk, and this distance is smaller than or equal to the distance between x and m sub I for all of the i's going between 1 and k. Hence, our new point is always going to be a new distinct point. So it is distinct from M1, M2, all the way up to MK. So we can always find a new point. And that means we can find a set M1, M2, M3, and so on. And I'm going to rewrite this as the set of mi's, such that I goes from 1 to infinity, where all of these guys are distinct from each other. And because they're all distinct, that says M has an infinite subset, and hence M is an infinite set itself. And that completes our proof.